In this video, we're moving on to a new section, section 5.3 in your book, where we learn something called the evaluation theorem. One of the more exciting, I don't know, don't judge me, maybe that's not the right word. One of the more interesting, one of the more impactful, maybe, sections of your book. What makes it so interesting, impactful, maybe even exciting, is that it connects the two main topics we've learned so far in this class. So remember, we spent a lot of time building up to 5.2, where we learned how to calculate, not estimate, but calculate the area underneath the curve between two bounds. And we even learned that we can write it this way, the integral from 2 to 5 of x cubed dx. We calculated that to be 609 divided by 4. Here's that 609 fourths. Maybe you remember it being a lot of work. If you don't remember it being a lot of work, let me kind of refresh your memory. Remember all this stuff? It was pretty crazy to figure out how much area there was underneath this curve from 2 to 5. Anyways, after doing all that, we got kind of a palate cleanser moving back to chapter 4, where we learned about antiderivatives. And what we learned in 4.8 is that this notation, which looks surprisingly similar to this notation, it's almost the same except we don't have the numbers here and here. Anyways, that this notation right here is asking you to find an antiderivative of this function x cubed. Or I guess more specifically, it wants the general antiderivative, a family of functions, so that if you took the derivative of any member of that family of functions, you got this as your answer. And this was a little bit easier depending on which function you were given. For a function as basic as x cubed, it really wasn't that bad. Hopefully everyone's to the point where they can look at this and they'd be like, yep, 1/4 x to the 4th power would be the antiderivative of this guy. It turns out these two things are connected. And I'll explain more about how it kind of makes sense that they're connected, but maybe the more obvious way to explain how they're connected is, well, they look a lot alike, right? I mean, they almost look the same, so there's not really any reason they shouldn't be connected. And my argument for why they shouldn't be connected is this is the area underneath the curve. This is the antiderivative. As far as we know, those two things have nothing to do with each other. There's no reason to think there'd be any connection between the two of these. But watch this. If we refer to the function in question here as f of x is x cubed, then hopefully you're comfortable with this notation, capital F of x, just denotes the general antiderivative of this function. So as this statement right here is saying, the antiderivative of x cubed is 1/4 x to the 4th power. What if, just for the hell of it, you decided to evaluate f of 5? Capital F of 5 here. And you're like, why would I do that? Well, I don't know. Capital F is the antiderivative, and there's a 5 written right here. Let's just play along and see what happens. I mean, it's easy enough to evaluate f of 5. Just copy this function right here and change all the x's into 5s. Probably the hardest part is figuring out what 5 to the 4th power is. See, 5 times 5 is 25, times 5 is 125, times 5 again, I think it's 625. So we get 1/4 times 625. We get 625 fourths, and if you want, plus this constant. All right, that's kind of similar, but it's not quite the same. I don't see what's going on. Well, there's another number. Right, we got this 2 here that we haven't done anything with. Maybe just for the hell of it, we'll stick that 2 into this function and see what comes out. Well, let's see, 1/4 times 2 to the 4th power. 2 to the 4th power, 2 times 2 is 4, times 2 is 8, times 2 is 16. So I guess that's 16 fourths. And 16 fourths is just 4, but I'm going to leave it as 16 fourths for now because I want a common denominator between the two of these guys. And the reason I want a common denominator between the two of these guys is you might notice that 625 minus 16 is exactly 609. Whoa. What just happened there? It almost looks like we could get the answer to this absurdly hard problem that involved limits and, I don't know, days and days and days of videos to work up to and some pretty intense formulas, good old Fallhaber. It almost seems like we could get this answer without doing any of that work. It almost seems like there's a shortcut way to get this answer that only involves antiderivatives. I mean, maybe it's just a coincidence, right? Maybe this is just some coincidence I'm stumbling across to mess with you. Turns out it's not. The formal statement of the evaluation theorem says that as long as your function is continuous on this interval from a to b, then the area underneath this curve f of x from a to b is given by just looking at the antiderivative of that function evaluated at the endpoints. And frankly, that's amazing, right? How much area there is underneath the curve, it seems like it should be dependent upon all the values of x between a and b, right? Picture this. Here's your function f of x. Here's a, here's b. The area underneath the curve here, all this stuff, we can figure out by just taking the antiderivative of this and looking at this point A and at this point B. We don't have to look at any points in between A and B, and yet we can calculate this whole area under there. It's amazing. It's called the evaluation theorem, and it'll be the single most important thing you learn in calculus. It'll allow us to answer this fundamental question of calculus 2, how much area is there under a curve, in a way easier manner, without doing anything with all these limits and all this crazy work that we did in 5.2, and instead just using antiderivatives. Couple comments here. The evaluation theorem, it is proved in your book. It is pretty amazing that these two things are connected. And there's a proof that they're connected in your book. It's on page 356. It's an interesting proof. It uses these thing called telescoping sums. Whatever. I'm not going to bother trying to prove it in this video. I am going to make kind of a half-assed argument about why they might be connected though. We've seen a couple examples in homework in this class. The last question on the antiderivative homework, and what we saw in this problem is that because in Calc 1 we learned that acceleration is the second derivative of a function that gives position and velocity is the first derivative of a function that gives position, it kind of makes sense that velocity would be the antiderivative of acceleration, and maybe more importantly, that position would be the antiderivative of velocity. Right, we saw a connection between the position of something and the velocity of something, namely that the position was the antiderivative of the velocity of that something. But then if you go all the way back to, I think it was the 5.1 homework where we're estimating area with rectangles, and you look at the last question on that homework assignment. On that homework assignment, we had this function, and the function gave us velocity, so it gave us the speed. And what we figured out is if we could figure out how much area was underneath that curve, it would give us the distance, the change in position. So we saw this connection here between speed and position, and we also saw this connection here between speed and position. Here the connection had to do with antiderivatives. Here the connection had to do with the area underneath the curve. So I guess maybe it's not completely shocking that there's some connection between these two. It's still pretty amazing though, and it still will be very useful for the rest of this class. To try to get you to appreciate this as much as I appreciate this, I am going to take you to what is probably the worst homework problem I have assigned to you all term. In 5.2, when we were learning about the definite integral, you had a bunch of problems in here that probably took you a little while towards the second half here, 5, 6, 7, and 8. Let me find an especially bad one. This one, ugh, I bet you hated this thing. I bet question 7 was just the worst, right? You probably spent 30 minutes if you were lucky and got it all right the first try around. Let me show you how we can now answer this question. To evaluate this definite integral from 2 to 6 of x squared plus 3x plus 5, we can simply apply the evaluation theorem. All we have to do is figure out what the antiderivative of this function is. So in this case, f of x is x squared plus 3x plus 5. So therefore, capital F of x would be, well, depending on how good you are with antiderivatives, you might be able to just look at this and tell that its antiderivative is 1/3 x cubed. And then for this term, we can call it 3/2 x squared. And for the last term, we can call it 5x. And if you need more help on that, you can go back to 4.8 where we learned about antiderivatives. For now, I'll just assume that you know this. And you're probably tempted to tack on a plus c here. And I guess technically we should tack on a plus c here. But for the use of the evaluation theorem, since we end up subtracting two things, and each of those things have a c in them, the c's end up just canceling out. So we don't really even have to worry about that. But maybe for the sake of good notation, I'll put it in. We need to know what f of 6 is, capital F, and capital F of 2. And if we could figure out these two numbers, we'd subtract them and we'd be done with the problem. You might want to just pull out a calculator for this, but let's see, 6 to the third power, 6 times 6 is 36, times 6 is 216. And then 216 divided by a third, I think that ends up being 72. But whatever, this is stuff calculators can do. 36 divided by 2 is 18 times 3, I think that's 54. And then 6 times 5 is 30. And then we have the plus c, but I'm going to completely ignore that. And then let's evaluate, I guess we could add up these numbers. Let's see, that's 102 and 54 more is 156. If I'm adding these up right, I'll know soon enough. And capital F of 2 I get by just plugging 2 into this capital F of x. So 2 cubed is 8, and 8 times a third is 8/3. And then 2 squared is 4, and 4 times 3/2 is 6. And then 2 times 5 is 10. So I get 16 and 8/3. Ugh, that's kind of ugly. I probably should get a common denominator and solve it all that way, but I kind of don't want to. I'm going to say 16 and 8/3 because I'm going to subtract these two in the next step, and I think I'll be able to figure this out without actually getting a common denominator. If I do 156 minus 16 and 8/3, well, 156 minus the 16 part gives me 140, but I still have to get rid of the 8/3 part, and maybe now I can get a common denominator to work out a little bit nicer, is 420 over 3. And I subtract 8 over 3, and I get 412 over 3 as my answer. And again, all of this is just because I don't have a calculator handy. You probably way back up at this step could just do a number minus a number and get this. And I don't care if it's decimals or fractions or whatever. At any rate, 412 over 3 is the answer that I'm coming up with just using antiderivatives. Let me now go back to this homework problem. And since I have the power of the teacher, it lets me click on these and look at any of the answers. This horrible problem that took you so long to do, looks like the answer was 412 over 3. This will always work, this evaluation theorem, and it'll make your life so much easier. You will come to love this evaluation theorem. One last thing I want to show you, I'm going to use this exact same example. It just has to deal with notation. And then the next video, we'll do a bunch more examples. This is kind of awkward to write, right? Like I'm writing little f of x, capital F of x, then f of 6, f of 2. It's not like one long string of logic. It's kind of a bunch of different parts where I'm jumping around and then I'm subtracting things. It would be nice if there was one continuous way to write up these steps. And it turns out there is, you just haven't seen it yet. When you're asked this question, you could skip the step where you write little f of x and capital F of x. I mean, you still need to know what capital F of x is, but what I can say is this is equal to, and then I can immediately take the antiderivative of this. So that's my 1/3 x cubed plus 3/2 x squared plus 5x. And you can leave off the plus c if you want, because we're not even going to end up using it because when I subtract capital F of 6 and capital F of 2, it'll cancel out. So the standard way to write it is to write this without the plus c, and then put a line over here telling your reader that you still need to evaluate this antiderivative from 2 to 6. In other words, you're going to plug 6 in here and then get your answer, and then you're going to plug 2 in and get your answer, and then you're going to subtract the two of these. So this is equal to this once you understand what this bar with the 2 and the 6 here mean. So then you can just go through and plug in the 6 and plug in the 2. And so we did that already. If you plug in the 6, you get 72 plus 54 plus 30, which maybe later you can figure out as 156. You don't need the parentheses here, but I like them. I think it makes it more clear what you're doing with your work. And then you subtract from that what you get when you plug in 2. And here you do need the parentheses because it's important that you subtract 8/3, 6, and 10, that entire sum. So this is equal to this. And now I just need to add numbers and subtract numbers. And when you do that, I think you'll find that you have 412 thirds. And so the advantage to writing it this way over this way is instead of just having a bunch of little pieces floating around that you put together, we have a bunch of equalities. This line is equal to this line, which is equal to this line, which is equal to this line. So this original question has this as its answer. So this will be the way we end up writing these up. I just thought it might make more sense to kind of do it in an intuitive way the first time around. I'm going to end this video here. I just wanted to show you that one example. We'll go through and do a lot more examples in subsequent videos, but this really was just meant to be an introduction.